Okay, so I'm going to have two parts to this talk, and if I push the button, it doesn't seem to be working. Yes. Is the down one? Aha. Okay, so I'm going to make just a few remarks about climate change and where we're heading before I hope to give you where science and technology can actually give us better options than we face today and give policymakers better options. So I just want to make just a few points. A lot was said about climate change, but I want to emphasize that what we're seeing is certainly not like what has been happening in the last 10,000 years, which is a record of the carbon dioxide in the atmosphere, and this is where we are now. Now, if you look at this, you might suspect that this might not be a natural phenomena, but indeed it's more than that. The emissions that we see, minus what we know is very quickly absorbed by land and ocean, actually matches quantitatively the amount of carbon emissions estimated that humans put up. In addition to that, the dilution of carbon-14 to carbon-12, which means that the carbon being introduced into the atmosphere had to have been sequestered for many carbon-14 lifetimes, which are 5,700 years. So that means it had to have been sequestered for many tens of thousands of years. So these are the smoking guns that say this is not a natural phenomena. This is sequestered carbon being emitted. And that's the most compelling evidence that this is due to humans. Has been said many times, but we're repeating that in order to achieve the UN goal of being less than 2 degrees, all of carbon emissions from agriculture, power generation, transportation, everything has to go negative by 2070, 2080. So this is a daunting task, and I'll return to what was just said about what we need to do. At the very end, this is a much more likely scenario, which means we're really heading to maybe 3+ degrees. All right, so this is the UN goal, 2,900 gigatons of carbon dioxide, and there's the founder, this has all happened within the last 65 years, 3/4 of it, so it's a very recent phenomena of this cumulative emissions. And to remind you of what the father of Taoism said, if you don't change direction, you will end up where you're heading. And we are heading across that line in the next 20 years based on just current rates. So the other thing is that once the carbon dioxide is in the atmosphere, or greenhouse gases are in the atmosphere, half of it gets absorbed very quickly, but the other half circulates with several lifetimes. About the mean lifetime is about 10,000 years. That's, of course, an estimate. But don't think 2100, think 12,100. Just to, it's a different decimal place. All right, now let me tell you the good news of science and technology. First, as been pointed out before, a large fraction of the greenhouse gas emissions are actually from agriculture, land use, including deforestation and forestry. But the other thing is that we have to realize that half the habitable land in the globe is already used for agriculture and grazing. And so we have to look at increased productivity to feed a growing population and a growing, more prosperous population. And so I'm going to spend a little time on that. Now, in that, there is a deep suspicion in Europe and Africa of genetically modified plants, but I have to remind you that we've been genetically modifying plants and animals for over 4,000 years. The early example is the difference between ancient corn and modern corn. And if you start looking at these ancient corns and modern corn, they really look different. That's due to genetic engineering called breeding. Okay, if you look at the livestock we raise, the full circle are the natural lifetimes of the animal, the cattle, the pigs, the chickens, and the turkeys, but they're actually slaughtered in a very small fraction of their natural lifetime. And if you think about how we've engineered these animals to grow, it's astounding. A pig of only 22 to 26 weeks when the time of slaughter already weighs 280 pounds. Forgive me for using pounds instead of kilograms, but just divide by 2.2. So the other thing you have to remember is that if you look at the entire biomass of all mammals in the world, 96% are due to livestock and humans. The rest of it, lions and tigers and bears and whatever else, is only 4%. So we have not only genetically engineered the livestock and the plants, we've actually taken over mammal life in the world. All right, give you an example. Domestic turkeys, slaughtered after 3.5 months, you get to buy a 12 to 14 pound turkey in the supermarket. The fully dressed turkey, feathers, head, and feet, weighs more than 14 pounds. These turkeys are so artificial, they can no longer breed. They're actually bred by artificial insemination. And so if you consider these turkeys and compare them to wild turkeys of unknown ages, not 12 or 14 months, they look very different. Of course, here's an example of some wild turkey, and we know exactly how old it is, at least the 101 proof stuff. In any case, if you think of livestock, and if cattle, beef cattle and dairy cattle were a country, the amount of greenhouse gas emissions would exceed any country except China and the United States. The greenhouse gas emission from just cattle and dairy cows. And that 4.6 gigatons per year of carbon dioxide equivalent, if you compare it, that bottom color yellow is the entire EU 28. All right, so this is the significant part of greenhouse gas emissions. This is why very innovative companies are trying to make things that taste like ground hamburger, which is half the use of cattle beef, to be grown by vegetables. And these are actually reasonably good. I've had several versions of what's called the Impossible Food Burger. It was founded by a very distinguished biochemist at Stanford who quit his job, Howard Hughes, medical investigator, and he said he wanted to do something good for the globe. He knew biochemistry. So using vegetable-derived hemoglobin-like molecules, it tastes like meat because there's the blood constituent. He puts myosin molecules, which are found in muscle, in there, so when you cook it, it sizzles and juices are released. So it acts and cooks like meat, but if you don't want to cook it, it also makes a very good steak tartare. So, but there's more to it than that. You can also improve the productivity of plants. First, we want to replace a lot of the meat with meat-like substitutes, which are an order of magnitude or more less resource-driven. But also plants are now being able to make their own fertilizers. So this is a corn plant, and an innovative company called Pivot Bio is introducing microbes where they get the microbes to talk to the corn, and the corn, like legumes, now on demand says, feed me more nitrogen, ammonia-based fertilizer. The microbes make it and feed them. And so this is now undergoing final field testing, will be introduced commercially next year. So the plants themselves will require less energy inputs. But in addition to that, you can look beyond the plants, beyond substituting meat, and say, what about all the bioresidues, the half the corn stover you have to put back in the ground to replenish the nutrients, but much of the wheat straw, rice straw, and the corn cobs are now burned or buried, not converted into methane for reuse. Is it possible to actually get these agricultural residues in bio-based plastics and chemicals? Now, why do you want to do this? It's because if you look at oil, 85% of the oil is used for energy, mostly transportation. It's too valuable to burn to generate electricity, and that's a $3 trillion market. However, 15% of the oil is actually used to make chemicals and plastics. The plastic and chemical industry is called the petrochemical industry. There are virtually no other chemicals except for petroleum and now natural gas. It too is a $3 trillion market. If you can find a substitute for plastics and chemicals, you devalue oil. If you devalue oil, you're more likely to leave it in the ground. So this is actually a very important step. And so if you think about what we did in the last century from 1900, and you think about the amounts of materials we use, woods, natural rubber, shellac, sulfate, these are all natural products. And then what happened with the discovery of oil is that you've got a lot of compounds used very heavily, replaced many of the natural products. Just beginning now are what we call bio-based plastics, but it's at a very, very low level, polylactic acid and other things like that. The question is, can you make these bio-based plastics competitive or oil-based plastics at $80 a barrel? That's the question. And so the answer is there may be a way. Now, for full disclosure, I'm the board of directors of this company, but it's a company that uses the ability to look at all the genes of a microbe and vary them, the ability to actually automate it so you can vary them with good reproducibility, and then use machine learning methods and infrastructure to actually give you better microbes. How well does it work? It's pretty good, because here on the blue you see a big ag bio-based company making material that's used commercially at commercial scale, and over the years 1 through 10 and 12, they're slowly improving the productivity of the microbes. And this company, starting with the robotic machine learning and deep knowledge of how to explore the genes, we went in from a standing start much below the productivity of the microbes being used commercially to 20% better. And so the progress now using the artificial intelligence and robotics is actually quite remarkable. What's the most remarkable thing is if you look at the genes, and there were about 14 genes that were changed, you could say, a biochemist would say, oh, those genes on the extreme left-hand side were on the metabolic pathway. And off the metabolic pathway, once you see that those genes are vital for it, you say, aha, I think I understand why. Then there are another 5 genes that said, why should this have anything to do with this metabolic pathway? And there were 3, and we didn't even know what the genes did, what the proteins did. And so this is where unstructured machine learning is actually quite useful, because we don't actually know what most of the genes do. So the opportunities are immense for eco-friendly bug sprays, for wound-healing hydrogels, for thin to high-value plastics, and there's now a growing realization that microbial biosynthesis you start with the high-value products, but you begin to replace oil in these materials. Okay, now, a few other good things. Renewable energy costs are dropping. They've been plunging the last 5-10 years. In the best sites in the world, without subsidy, they're less than 2.5 cents a kilowatt hour, and there's every expectation to believe in those very best sites, the windiest sites, the sunniest sites, it will be less than 2 cents a kilowatt hour by 2030. Now, it's important that they be less than that, because actually renewable energy has to be about twice as cheap as fossil fuel, because all the backup for fossil fuel, including standby power, energy storage, and transmission distribution systems, are part of the cost of fossil fuel once it gets to be 50–60% of energy. And that you have to appreciate. So but the good news is it's going to happen. It's going to get twice as cheap if you have the right systems. Energy storage is one of them. Here's my favorite picture of a battery. When the wind blows, you use the energy. When you pump it out of the ground, the energy is stored as pumped water. In the developing world, it's not only pumped water, it's disinfected water. And then you drink the water. And so this concept, which we knew 200, 300 years ago, should be revived. We can learn the technology again. If you think of pumped storage capacity around the world, in 2014, Japan, believe it or not, led the way, followed by the United States and China. In China's plans, by 2020, will be 40 gigawatts and hundreds of gigawatt hours of pumped storage. and by 2030, they'll be at 90 gigawatts. So by 2030, they plan to have as much pump storage as the rest of the world combined, and more, because they recognize how vital large-scale seasonal energy storage is, and this is the only form of seasonal storage we have. Electric vehicles, dramatic change in prediction of electric vehicles from 1 year, 2015 to 2016. You see these predictions from 2020 to 2040. The newer prediction says we've underestimated how electric vehicles would be adopted. And you can ask the question why, as there's such a dramatic uptick in prediction. It was not due to a breakthrough in batteries. It was due to a new understanding of the health effects of internal combustion engine cars. This is Beijing on a bad air day, where now we're beginning to discover that PM 2.5, that is to say particles less than 2.5 microns in diameter, are especially deadly, that a large epidemiological study going over 12.8 years, following 300,000 people, British people, because the data in China and India were not reliable enough, found that for every 5 micrograms per cubic meter of these particles, you have an 18% higher chance of getting lung cancer. The average air in Beijing today, it's gotten better. It's now down to 76 micrograms per cubic meter. Delhi's about 400. So this is like smoking 4 or 5 packs of cigarettes a day from day 0. The World Health Guidelines for clean air is 10 micrograms per cubic meter, and so there's now a discussion, is 36% higher chance of getting lung cancer considered clean air? And so more epidemiological studies are occurring, but the risks are more profound than we thought just simply 5 years ago. Batteries are being improved. I'm collaborating now with a young colleague, Yi Cui at Stanford, first with silicon anode, but the ultimate would be lithium metal and sulfur. Why sulfur? Because it's really cheap, and the energy density can be 4 or 5 times greater. Also concentrating very hard on getting a battery to charge a 300-mile range, but maybe 120 miles in 5 or 6 minutes. If you can do that, then the show is over. You go to electric vehicles. Also, we're doing research on how to convert cheap electricity into chemicals, notably hydrogen. I don't have time to go through it. Well, maybe I do. This is electrolysis that you might have learned about in high school. You get oxygen on one side, you get hydrogen on the other side. But if you examine atomically what's happening, you have a catalyst, and let's say you're making hydrogen or oxygen. You form a bubble, it takes energy to actually expand the bubble, and as the bubble expands, it actually blocks all the other catalytic sites. So bubbles actually slow up the electrochemical reaction. And what we found is if you put the catalyst on a cheap, very cheap polyethylene film, so the oxygen and hydrogen, when they form, they're only a few molecules away from escaping as a gas. And so if you do it this way, and it's agnostic of the catalyst, what we find is for the exact same catalyst on a metal electrode, you need 5 times more energy to produce the same amount of hydrogen. Okay, so this is going to make electrolysis much cheaper. The combination of cheap electricity and much more efficient electrolysis can actually make chemical fuels a reality. How do you ship and store hydrogen around the world? Again, very exciting research being done. This is by Peter Wasserscheid in Erlangen, Nuremberg, and he's found that if you take these molecules on the left-hand side, these 3 benzene rings, and hydrogenate, you can get 6 hydrogen atoms onto that organic liquid. If this is the density of liquid hydrogen cooled to 20 degrees Kelvin, you find that it's actually higher energy density than liquid hydrogen, but it stores at room temperature, and it ships at room temperature, which means you can put it on a slow tanker. Now, much does it require to ship liquid fuels around, for example, crude oil, halfway around the world and store it on shore so you have energy security? The answer is 2 cents a gallon. So shipping costs and storage costs of liquids are virtually free. And so that's why you want it to be in liquid form. Okay, so I'm going to skip this. I'm out of time. There's carbon capture. This is the best way of carbon capture, photosynthesis. Take the residual plants and turn them to your useful fuels and chemicals, and then sequester the rest of the carbon dioxide. How much is captured by photosynthesis? Twice as much as all human emissions per year. So, and that's only the photosynthesis from agriculture and grasslands that we actually cultivate, not from Brazilian rainforests. So it's an enormous amount of photosynthesis that we actually control. And so let me just stop by showing this iconic picture called Earthrise. Now, the astronaut who took this picture said, we came all this way to explore the moon. And the most important thing is we've discovered the Earth. Christmas Eve, 1968. Since that time, we've discovered we're changing the climate of the Earth. It is largely due to humans. And look at the moon. Not a good place to live. No water. Lethal dose of radiation if you live on the surface of the moon. That planet looks pretty good. And notice something else. There's nowhere else to go. Thank you.